This is from NIST 2010. In a repeat of one of Michael Faraday's classic experiments, a solenoid of length 10 centimeters with 200 turns and radius 1 centimeter is surrounded by another solenoid of the same length but with 400 turns and radius 2 centimeters. The two solenoids are not in contact. A current is switched on through the inner solenoid. Suppose that the current increases at the rate of 100 amperes per second during the switch on. What is the EMF induced in the outer solenoid? Assume that a current carrying solenoid has no magnetic field outside it. Okay. Let's draw the figure first. Let's draw the figure. So we've got two solenoids. One solenoid has length 10 centimeters, radius 200 turns, say inner. Length 10. Total number of turns, so let's call it n. 200. Radius 0.01 or 10 raised to minus 2. It is surrounded by another solenoid of the same length. Okay. 400 turns and radius 2 centimeters. The two solenoids are not in contact. So let us show the inner solenoid in red color. Then we have got that outer solenoid with twice the radius. Now look, it has more turns of course, but I have shown them with less turns. Okay, so outer is green, inner is red. A current is switched on through the inner solenoid. Suppose that the current increases at the rate of 100 amperes per second during the switch on. What is the EMF induced in the outer solenoid? Look, they have given us the rate at which the current increases, which means we can now use the formula that epsilon is equal to negative m di by dt. So all we need to determine is the mutual inductance now. Raise your hands if you understand that. Okay, fine. Okay, mutual inductance into the rate at which the current increases. Okay, now how to find the mutual inductance? You know the formula. N phi b by I is the formula. Okay, so suppose we assume that current I is flowing through the outer solenoid, doesn't matter, but let's assume that it flows through the outer solenoid. So we now need to consider the total number of turns of the inner solenoid, so that is 200. Magnetic flux is there, field will be produced by the outer solenoid, mu naught is 4 pi into 10 raised to negative 7. Okay, mu naught is 4 pi into 10 raised to negative 7. Number of turns per unit length of outer solenoid. Outer solenoid has 400 turns. Its length is 0.1 meter. We have to divide that, so it will be 4000 turns. Now current I, we don't know the current, but that's fine. Now we have to multiply this by what? We have to multiply this by the area of loop of inner solenoid. So pi into radius squared. Radius is 10 raised to negative 2 meters. So this will be 10 raised to negative 4 meters squared upon it. Current will go. Current will go. Now what will remain? What will remain? Nice. Okay. Let's first collect the terms which is not powers of 10. So 4 into 2, 8. 8 into 4, 32. Pi squared into 10 raised to 200, so 2 minus 7, 4000, so plus 3 minus 4. Okay, let's see if I've not missed anything. 2, 4, 4. Okay, 32. 2 zeros, so 2 minus 7 plus 3 minus 4, that's right. Pi squared. Okay, fine. So that's 32 pi squared into 10 raised to what? 3 plus 2, 5. 5 minus 4, 1. 1 minus 6, 1 minus 7 is minus 6. Okay, Henry. And now we have to find out the EMF induced. So minus 32 pi squared into 10 raised to negative 6 into what? Current rate of increase, 100 amperes per second. Okay, so just take the mod now. Okay, so that's 32 pi squared into 10 raised to negative 4. Now if you know pi squared is approximately 10. Okay, so mod epsilon will be 32 into 10 raised to negative 3 volts. So that should be, and it's actually less than that, so option B is right. Okay, option B is right. Now, if you have this question, that just occurred to me now, that this expression for induced EMF that we write, okay, is it for a single turn? Okay, is it for a single turn or is it for the whole solenoid? Can you answer that question? The expression that we write, is it for a single turn or for the whole solenoid? Yes, why whole solenoid? Because while calculating that mutual inductance, we have considered all the turns of that inner solenoid. Got it? Let's come to the theory now. See that epsilon net, when we consider epsilon net, okay, in that we already incorporate it, right? So that's just the mutual inductance and not, so there's no need to again multiply it by 400, okay, or 200, whatever that number is. Got it? Okay.